Hey guys, welcome to another video. So today we continue and conclude the series on integration with recurrence under the extension 2 syllabus. So if you haven't already seen the first two videos, please go hit them up. The first one sets the framework. The second one touches on Trig related questions, which are probably the most common ones, and you'll see one today as well. But today's video really focuses on, now, some people call it harder. It's probably just more involved, and with more involved comes a lot more marks. So let's proceed. So I don't have any new theory today. We're just going to dive right into it and see the questions for what they are. So let's go. So this first question from Balcombe Hills. Now, it's a classic question where if you look at how it starts, right, it once again paints a picture of a recurrence statement there. Yeah, it defines IN, but what's really important for students to note is that normally when these questions are asked in recurrence, part one is usually prove the recurrence statement, and part two is use the recurrence statement. In this one here, I mean, part one is a classic, right? You still have that sort of prove recurrence statement, but part two, right? Now, what's interesting, and I keep identifying this to my students, is for this type of question, the relationship between the original IN and this guy here in the green box is a bit different, right? One's trig and one isn't. So somewhere down the track, we're going to have to transform the question at play into an expression that represents I5, I4, I something, right? That's part of the game. So, but firstly, let us prove this identity statement, recurrence statement here. So let's go forward and do what we did previously. So this one has limits as well. So normally with limits, unless the limits are not pretty, it normally simplifies things right down. So sine theta. Now, guys, we've done this before, right? We've done this before with sine, and I said to you with sine, we break it up by, in the last video, and once again, if you haven't seen that, please do. If it's sine, we break off one sine, right, to do by parts. So this is an example where I say that Lie8 fails, right? This one's sine theta times by sine n minus 1. In that they're both trig expressions. So you come back to the principle of Lie8, where on one hand here, maybe I should have put in minus 1 first, but that's u, and this guy together are dv, right? So off to the side. Yep. So if I let you, so the principles of Lie8, like I said, it basically gives you an order to differentiate. However, it's actually the reverse order of what's easier, what's harder to integrate, right? So in this case, we're going to let sine be the differentiable statement, where du bring down the n minus 1. Knock off one from the power and then multiply by derivative as well, d theta, and then dv equals to sine d theta, where I know that integrating sine integrates negatively, right, minus cos theta. Right, got my tools. Therefore, in now with the limits, uv u times v, so that's negative cos theta sine n minus 1 theta. I'm hoping that the limits here take care of this. So pi 2, cos pi 2 0, that's 0. Okay, sweet. This whole thing 0 gets zeroized, and then minus. Now, it'd be v times du. You can see there's a minus there and a constant, so take that out, right? Same limits, pi on 2, and then the cos times cos becomes cos squared. I'm going to use, just like in the last video, some trig identities for that, right? So this guy here, we know that that equals to 1 minus sine squared. Sweet. So, and also I know that subbing the limits there, that guy gets zeroized. So you get a nice clean expression with only one term. That looks like this. 2. Now expand that, so sine n minus 1. Oh, sorry, n minus 2 rather. theta minus, and then the 2, so the fill's in the gap to make it sine n theta, d theta, and just be clear, that guy there looks like the original, right? But within my one, so that guy there is I n minus 2, and that looks exactly like the original function. It's in, right? So we're going to put that in, take it over, factorize, make in the subject, right? And then get the full 3 marks. So then it'd be in minus 2 minus in. Guys, expand that and you get like n minus 1 times in minus 2 minus n minus 1 in. So at this point, we basically sort of bring them over the fence and group them. So that becomes what? N minus 1 plus 1 is that n? Let me just check. Yep, perfect. Just n. So when I take it over and I factorize, it's like 1 plus n minus 1 equals to n minus 1 minus 2. That's n. So therefore, a recurrence statement has been shown. Now that's 3 marks, right? Now, normally part 2 on this is worth like 1 or 2 marks, but this one's worth 3 marks because it is unclear. Normally they go, can you please find IN, I3, I4, I5? This one, unclear, right? It isn't clear what this is right now. I need to express that as I something, right? I don't know what it is. So maybe I'll start here. I'll probably run out of space, but part 2. So this question, firstly, the limits are different as well, right? And I mean, that's a dead giveaway that you're going to need something, right? And the technique at play here is trig sub, right? We're going to target a variable and let x, right, equal to that, right? An expression, a function. We're going to let x be a function that simplifies this whole thing. Now, if you've done this before, we know that if I let, when it's 4 minus x squared in this format, right? If I let x be 2, 2 is good because when I square it becomes 4 and I can factorize for it. So it'll be 1 minus something, right? And I know using trig identities, I have 2 options. I either put a sine or a cos here. Now, I'm going to put a cos. Because if you think about where you're 1 ahead, right? Yeah, if I was to, now maybe I'll rub this off in a sec. But if I put in 2 cos into here, what's going to happen is I get 4 minus 4 cos squared, right? Inside this sort of bracket, 5 on 2. The 4 is factorized out, right? Of the bracket, and I get 1 minus cos squared, right? To power 5, I'll leave it to 5 on 2 for now, right? Just to illustrate. And then that becomes 4 times sine squared. That's good, right? Because I want to basically break this expression down into sine squared, because then sine allows me to use my recurrence statement, right? So that's why I'm using cos, because 1 minus cos squared gives me sine squared by itself. So that is the absolute reason why we're using cos instead of sine. So once we go here, now there's a couple of things that happen. Firstly, the limits get changed, right? So when x used to equal to 2, now equals to, so if x equals 2 goes over, cos theta equals to 1, and that is 0, right? So not u, theta, right? Similarly, when x equals 0, we know that if x equals 0, cos theta equals 0 at pi on 2, right? So they're the new limits. Let's differentiate both sides. Dx equal to 2 differentiate, right? So minus sine 2 sine theta. So it's a triple sub, isn't it? So let's see. We're going to sub this guy into the value of x. We're going to sub this. Oh, sorry, I didn't have that here yet. D theta. We're going to sub this guy into dx, and we're going to sub the limits into here and here, right? To get this guy equaling to limit of pi on 2, 0. Now 4 minus 4 cos squared, which we know is 4 times sine squared, 5 on 2. multiplied by -2 sine theta d theta. Now that looks complicated, right? It looks a bit intense, but that's the whole point of doing these questions. So I want to show you some intensity here, right? Look how nicely it cleans up. So the 4 factorize out. Now, a few things actually. Yeah, my students, for some reason, some students tell me that they've never seen this before. But when there's a minus, right? Because if you take out the, when you sub in the limits, there's always top limit minus bottom. But if I factorize a negative out, I can actually cancel the negative and swap the limit order around, right? So this limit and the order of, sorry, this negative and the order of the limits can cancel out and swap around. So it becomes 0 pi on 2, right? And that's gone. Now I'll take out a 2 as well. Now, from this expression, I've got 4 sine squared to the power of 5 on 2, right? Multiplied by another sine there. D theta, guys, this is nice now. Now, that 5 on 2, so square root's that, and powers of 5, that's 32, right? The constant, that's 64 outside, so I'll take 64 out there. And the limits are beautiful. Now, sine square times that, the squares cancel out, and then for power 5 times by another one, that's power 6. And there it is, right? There it is. So if I put a little blue box around that, that looks exactly the same as my initial recurrence statement, but with a 6 there. So this guy here is I6. So what I'm finding is the value of I6, and then I multiply it by 64. That is now my question. So all that work theoretically is worth about 1, maybe 1.5 marks, right? Because it now gets me down to what I really need to do to find my recurrence. What I really need to use a recurrence for, right? To find the value of I6. So let me delete that for this one, and let's pop over here now. So the question now is I6, right? I'll find I6 and then I'll pop it back in with the 64. So let's go I6 first. Using recurrence, right? I go, so this is when n equals to 6. It'll be 5. I'm just using this guy up here. 5 minus 1, sorry, 6 minus 1 is 5 on 6 I4. Yeah, and then I4 equals to 3 on 4 I2, and then I2 equals to 1 on 2 I0. Guys, let's do I0. So, and then off to the side here, I0 equals to integral 0 pi on 2. Obviously, it's sine power 0 x dx. That's just 1. So pi on 2 minus 0 pi on 2. Yeah, sweet. Let me make sure that's right. Yep, pi on 2. So sub that and backwards populate that. So, and once that goes in, I2 equals to pi on 4. And then once that's done, backwards populate that P. And I4 would be 3 on 4, or 3 pi on 8. And then backwards populate that up here. I6 equals to, what's that guys? 15 pi, so just 5 times that's 15, that's 48. That'd be simplified. I think it can be actually. 3 and 6, yeah, okay. Cleaner than that. So it becomes like, let's go 5 on 6 times 3 pi on 8. That and that. 2 and 1, so it becomes 5 pi on 16. Now, and then my final answer, multiply that by 64. So therefore, the integral of 0 to 2, what's my question? Yep. Of 4 minus x squared, 5 on 2, dx is equal to 64 times 5 pi on 16. 64 divided by 16, what's that goes? 20? No, sorry, 4, is it? Yeah, 4 times 5, 20 pi. Now, what have I done? I feel like I've done a silly mistake somewhere because the answer's telling me it's 10 pi. All right, let's have a quick look. That's pi on 2. Yeah? That's good. In here, palm. Oh, palm 4. I think I said palm 4. Okay, let's fix that. At the 4, sub it in. That is 16. That's 16. That's 32. That's 32, and that's 10. Cool. Easy. Yeah, that's 16. 32, 32, 10 pi. Brilliant. There you go. Hopefully that was okay, apart from that silly mistake that I did. Hopefully you guys are better than me at doing that bit. So, I mean, it took quite a while, but that's 6 marks in an extension 2 test, right? So be ready to react to this. I told you that trig is really important. This one here, there's an extra element of difficulty with the trig sub, but it's so common, right? This question here, so common. So let's move on. I want to show you, a question that's worth quite a lot of marks, and because the multiple parts build up on it, once again, the I8 fails, and that's when you know it's a tricky question. So Normanhurst. So this one here, 9 marks, all right? 9 marks. So let's have a look at some of the questions. So first question there, bit of a build up, right? Can you please find the value of that? That's simple, I think, by parts, right? Nothing too tricky about that. And then it starts off with, let the IN equal to that, right? So it defines for you, yeah, an expression for IN. Good. Show that, okay, classic, right? And then hence show that, okay, cool. So some sort of, maybe it feels like from there to there, we have to do something by something recurrence. Oh, wait, this guy's odd. Ooh, that's tricky as well. Okay, let's have a look at that. All right, let's do first part. Now, the first one is just simple by parts, right? So I got ln 1 plus x dx. Now, using y8 actually works. So that's L, so that's, let that be x. And then 1 dx, so that's dv, right? So off to the side, if x equals to ln 1 plus x, then dx equals the derivative of that on top. So that's 1 on 1 plus x dx, right? Cool. And if dv equals to dx, then x equals to, so v equals x. And nothing too wow about that. So then therefore, ln 1 plus x dx, uv minus this guy times this guy. Yeah. And whenever you're doing this, hopefully you've seen this technique before. Nothing sort of rocket science. So plus 1 minus 1 to split that up. Just making sure that's right. Yep. Sweet. Get x ln a 1 plus x minus integral of 1 minus x. Just then quite simply ln plus x minus x plus ln 1 plus x. Let's see. All right. Just write it as box around it. Beautiful. All right, nothing too wow about that. Yep. Now, the important thing about this is why part 1, right? Why did I make you randomly do it by parts when they're doing a recurrence? It's because you need it now, part 2. Guys, this is your, I guess, training, right? Where in this case, the recurrence statement, sorry, the recurrence in, right, is given as xn. Now, always appreciate for, extension 2 questions where they give you an earlier part to a question. They don't just randomly do it, right? In this question, if you blindly applied the principles of Y8, you would say this guy's logs, this guy's algebra, and you would let u equal to this guy. But taking a step back, what's the principles of Y8 really about? they always let you equal to logs because that's easier to differentiate and very difficult to integrate. But in this question, part 1 specifically integrated that. So it's basically taking you down a path where you should actually let dv, right? You should let dv equal to this and let u equal to this, because I can actually integrate this using what I did in part 1. Does that make sense? So Lie8 principles, right, are more important than actually blindly applying Lie8 itself. That's important. So if your teacher, right, teaches you the principles of Lie8 as opposed to just blindly applying it, better, right? Better. So in this case, let u equal to xn, and that simply goes du, bring down the n minus 1 to the power times dx, and then, right, let dv equal to ln 1 plus x, right, dx, because then I can integrate that and copy and paste from above. So v equals to exactly that, ln 1 plus x. Right, use absolute values. I'll put the long one first, right? Log 1 plus x, and then minus x, right? And then got nice limits as well of 0 and 1. So therefore, in equals to u times v. Wow, that's ugly. Let me just make sure that's right. I guess so. Well, half the answers go away when I'm putting 0, so it shouldn't be that bad. Let's see. X. Plus ln plus minus x. 0 and 1. Minus, wow, this guy times this guy. What is going on? Okay, the n comes out. 0, 1. I'm hoping that it's just really nice when I expand it. I mean, that's just me wishful thinking. Let's have a look. Plus ln plus x. Okay, now when I use rainbows to expand this, right, x times that fills up the gap. That's x, and that's the original, isn't it? Right, that's the original. Good, because these guys, this guy multiplied this guy, that's in. This guy multiplied this guy, that's in minus 1. This guy minus this guy times this guy, it's a function I can integrate quite easily, right? So now let's do two things. Let's sub in the limits, and then I'll clean this guy up. So when 1 goes in, I get 1 times all of these with that 1's subbed in. So I'll skip that one. So 1, that's ln2 plus ln2 again minus 1, and then 0, right? So you just get that. 0 times anything, 0, right? Beautiful. And then minus n 0, 1. Now what do I have here? I got xn ln. I'll use brackets again to make it look like the original. Doesn't matter. Plus xn minus 1 ln 1 plus x, and minus xn, right? So this guy here, that's in. This guy here, that's in minus 1, right? And this guy here, I can integrate, right? Let's go now. So I go ln2. Maybe at this point, right, I'll expand it as well, just so I can bring the in over in the next step. Oh, there's 2 of these. So maybe I just go 2 ln2s minus 1 minus n times in minus n times in minus 1, and then plus n. The integral of that would be plus 1 with the limits of 1 and 0. Yeah, so it looks like it's just, make sure I'm on the right track. Hope I am. Yeah, okay, feels like I am. So let's keep going. Now, so at this point, I'm going to do 2 things, because if this is in, I'm going to go and bring these guys over. So bring this guy over here, factorize, right? So I get like in be 1 plus, that's a n plus 1. And then 2ln2 minus 1 minus n. Yeah, let me have a quick gander of what I have to prove. Yep, minus n. Okay, so I got that. And then this guy cleans up now. If I sub in the limits, it would just be 1, 0. So it would just be 1 on that, right? So it would just be n on n plus 1. Now, almost there. So I'm going to divide everything by n plus 1. At this point, a bit nervous. I'm a bit nervous. Actually, what do I have to prove? Oh, there's n plus 1 here. So actually on the right-hand side, I just leave it. Now, I'm a bit nervous because this looks a bit different here. However, you know, once I do the next step, you'll see that it all cleans up. So if I go plus 1 and I minus 1, right, just to clean this up because I don't want that n there, you'll get what you want, right? So you go, well, I won't go therefore yet, it's not conclusion. So actually I'll put the bracket first because that's what the question has it as. So this minus 1 needs to go away, and it goes away when I split this fraction up. Yes, because then it goes plus 1, there you go, and then minus that, right? And then in this case, 1s go away, and that's exactly what you want. So just check. Beautiful. They just put the fraction before the last limit, so the last space. Oh, I just need a little line left. So let me just move everything up a squidge. That's all I need. All right. Beautiful. Okay. And therefore, n minus n plus 1, sorry, in because of 2ln2, and then they put this fraction first, n minus n 1 n minus 1. Beautiful. Oh. Beautiful there. Done. So that's the recurrence part. Now, that's 5 marks so far. I haven't used it yet. Let's look at part 3. It's 4 marks. So might be a bit heavy. Let's have a look. Hence, show that. Now, a couple of things to note. 1, the 2ln2 is gone. Ooh, okay, somehow. And 2, there's no more. So on this side, it looks the same, right? It looks like I've done nothing. So it basically means that they've just simplified the right-hand side into this, right? That's all they've done. I say all, it's for 4 marks, right? So it just feels like they've just subbed in recurrence expressions, right? To a point that where the INs go away. So maybe the last term of I0 or I1. Now, n is odd, is telling. We'll see what that means, right? So the best way to start this is to start with a few substitutions. So part 3. Now, I don't know whether I fit here, but let's start here. So I know that my recurrence statement looks like this, right? I'll start there. So 2ln2 minus 1 on n plus 1 minus n I plus 1. First point I'm going to do is I'm going to sub in a value for I n minus 1, right? Now, the string of numbers might get a bit long, so I'm just going to go down here to, you know what? I'm not going to squash it, guys. I'm going to be amazing and give myself a lot of space, right? I feel like I need a lot of horizontal space. So I'm just going to give myself that sort of width so I can actually do my thing. So I'm going to sub in n minus 1 now into this recurrence statement, right? So let's see where that takes me. 2ln2 minus n plus 1 minus n, and then times. When I sub n minus 1 in, I've got 2ln2 minus 1 on. Now, that's n minus 1, right? N minus 1 plus 1, that's just n. And then minus n minus 1, I n minus 2. Okay, let's, oh, that's not n, right? Is it? So the first one where n is n, I think it's right. No, let me have to think about that. Because that n isn't supposed to be there. I know what I did. No. I just did a silly. So if you think about, sorry, I tried to do too much. I'll show you what I'm talking about. Let me park this over here. I'll come back for it. I actually should have done this. So let me get my point eraser. The n and the I n minus 1 actually belong together. Because if you think about it, if this statement here, right? Oops, if this statement here is when n equals to n, right? So this is when n. So for n minus 1, if I replace all the n's with n minus 1s, I get n I n equals to 2 ln 2 minus 1 on n minus n minus 1 I n minus 2, right? You can see that there's an n there, right? So this thing here is that. Actually, that n should not be there. So, you know what? Maybe I'll just do it like this a few times, just to not cause confusion. Maybe a bit easier. So when n minus 2, so if I sub in n minus 2 into the original, right, I sort of get like n minus 2 plus 1, that's n minus 1 in. So this term here, right, is 2 ln 2 minus 1 on n minus 1. You can see the pattern, right? Every time the fraction goes down by 1, every time the variable here goes up, the minus goes up by 1. So we're doing n minus 3. Right, so we're going to be subbing in. So I want to get down to a point now. This is telling me that n is odd, right? That is actually key. Why is that key? Because right now I can sort of see, right, in all my expressions, if n is odd, then the final number will be 0, right? That's important. Before I do that, actually, yeah, before I do that, let's start subbing it in, right? Let's start subbing it in. So if this green box here is equivalent to that, I'm going to sub this guy into here, right? And just be clear, then this guy here, oops, the whole thing is that. Yeah, let's sub it in, see where it takes us, right? Therefore, n plus 1 times in equals 2. I'm hoping that the 2 ln 2s all cancel out, especially if it's odd. I think it cancels out if it's odd. Yeah. Plus 1 minus bracket. Yeah. Because every time you sort of have like two numbers, the 2 ln 2s cancel out. Right? 2 minus 1 on n minus, and then it would have been the pink box, so the pink box gets reintroduced. 2 ln 2s minus. I just want to see where this takes me, right? N minus 1 minus n minus 2 and n minus 3, right? So you can see here the first two of these guys cancel out. And you're starting to get an expression that looks like minus 1 on n plus 1 plus alternating, right? That, and then say minus times minus times, that's a minus again on n minus 1. And let's see, minus times minus, that's a plus, so minus, that's 2. Now, as the pattern progresses, what you're going to see is this guy slowly going towards 0 or 1. Now, if n is odd, then it's probably going to go to 0, right? So I think the smallest number this can be is n equals to 3, right? Yeah, that's the smallest it sort of goes to, because when n equals 3, that's 0. So let's see where that takes me. So equals 2 minus 1 on, oh, sorry, there is a term here that I forgot. Let me just move this over here. And there is a plus 2 ln 2, right? But I reckon that 2 ln 2 would go away. Now let's see if this rule is right. So when n equals to odd, we're going to have a statement where, let's see, n equals to 0, n equals to 1, equals to 2. Yes, these guys will cancel out if it's odd. Let me have a think about how I would say that out loud. Let's see. So in the first iteration, so when n equals to n plus over here, when n is odd, right? So right now, when I start this statement, it is both odd and even, so it doesn't matter. But at the final state, like how many terms am I going to get when n is odd? When n is odd, let's see if there's if it is three of them. If I already start with one there, and I think I'm trying to work it out. Like I'm hoping, right, that when n is odd, this guy goes away, right, and then you just get the string of pattern here and this guy over here to deal with. I think that's fine. So let me see. Well, maybe not, because if n is odd, that guy stays there. Yeah, maybe it stays there, because if you think about it, if there's three terms, two of them cancel out, one's there. Maybe it's supposed to be there. That's fine, because I'm hoping that the integral takes care of itself. So, okay, good. Well, let's leave that there. Let's leave that there. Now, taking this down, right? I'm gonna shortcut this process to get this guy into a pattern, right? So then it goes. You can sort of see the pattern sort of goes down to +1 plus alternating -1 on n minus 2. I want to go down to 0, so it'll be like, and I'll hack this guy on the end as well. So blah 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 plus blah 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 blah. So I know that the very last term, when n equals 3, the last fraction is going to be a half, right? So when n equals 3, the last fraction is going to be half. The question is whether it's positive, negative. Now let's see. If it's odd, it's negative. So this will probably be like -1/3 and +1/2, and then minus, when that's 3, it'll be 1 times I0, right? Oh, and then there's a plus 2ln2 there. Yeah, I think that makes sense, right? Because then you can see the odd one there is negative, and the even one, oh, sorry, let me say again. You can see that, I probably did that wrong. That one's positive, because that's when n is odd. That's it. That's the even ones are negative, right? Cool. Plus. Yeah. Yep. Perfect. Minus I0. You know, maybe I just sub it in. So when n is 3, that becomes 4, but I don't really care about that. It's more the expression over there. Minus. N is, oh, that's the original. When n is 2, n is 1. Yeah, n is 1 minus half. You can see there, right? When n is 1, it's this guy minus a half, and then -1 times I. Okay, perfect. They're both negatives. I was just checking the signage, right? I was just checking the signage for this guy, the minus. All right, we're rolling. This guy now. This is my grand hope. Now, when I sub in, because right now I have a expression that looks very similar to this. Right, I've sort of got everything, right? That's everything there, right? That's a family there. There's a 1 here, don't have the 1. I'm hoping that when I integrate, 2 things happen. 1, the 1 comes in, and 2, the 2ln2 goes away, right? So let's see. That's the integral of I, now what's this again? So 0, so that's 0, that's gone, that's just the integral of the original, all right? So beautiful, that's just ln 1 plus x dx with the limits of 0 and 1, yeah? Is even limits? No limits. Okay, cool. Now, actually, has to be limits. Oh no, 0 and 1. Yeah. 0 and 1. Now I've already integrated this previous, so let me just do 2 things. 1, move this up so I get some space. Wasn't moving it up. And 2, what was my oh, I've got it from. Let me go up a slide. It's this guy here. Copy. And I'll just write x ln x minus. Okay, I'll just use my big brain and try and remember it. Right? So it's x ln x. Actually, did I not already do that in the last part with the limits? Yeah, I did it right here. Oh no, that's with x. No. So let's do it again. So it'd be x ln 1 plus x plus ln 1 plus x minus x, I believe. Quick look. X, boom, 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 perfect. Good memory. Okay. And then 1 and 0. I know I'm slightly off slide here, so I'm just gonna move back on slide. I think when you put in 1, you get ln2, so that's 2 ln2 again. And then putting 1, that's minus 1. And putting 0 gone, ln1's gone. So that's the answer. Now that's great, because you can see there, if there's a negative in front of that, 2 ln2 is going away, negative 1, 1. Okay, perfect. Therefore, n plus 1, got it, right? In equals to minus, actually let's do it in the order. So it'll be 1 minus a half plus a third plus also minus 1 on n minus 1 plus 1 on n minus 1 on n plus 1. Wow, right? So that was a little bit intense, yeah? And I must admit, even when I was doing it, there were parts where I had to refer back to the proof, right? The proofs above. So when you get down to this question, what I wanted to demonstrate to you is, in this case, it wasn't as simple as prove recurrence and then use a recurrence to find I5 or I6. It was like, still stick with the recurrence, but summarize the recurrence and remove the recurrence term to get an expression. Yeah, hopefully that makes sense. Look, I don't have, I want to end this video here. I don't have time to sort of cover the other question. Maybe what I'll do is I'll do another video on integration recurrence. Maybe I'll call this one part 3 and the other part, I'll call this one part 3A, I'll call the other one 3B. I want to explore maybe 1 or 2 other harder questions just to really get you exposed to the intensity of questions in this topic. Guys, hopefully that was a good video just to really show you the breadth of questions. And you can see 9 marks in a 4-unit paper. That's heaps, right? That's almost 10%. If you couldn't do this question well, your 4-unit marks in jeopardy, right? So guys, if you like that video, please give us a like, subscribe to the channel, tell your friends, and I will see you in the next video. Thank you.